Okay.
So hello everyone, welcome to this week's QTFMS seminar. This week we're delighted to have Alfred Shapere from University of Kentucky. He will be talking about his recent work on holography of free fields. Alfred Shapere, you can take it away when you're ready.
All right. Thanks for inviting me to give this talk. I've never given a talk in Turkey before. So I'm gonna, well, I'm going to talk about, title is Holography of Free Fields, but it will be a little more broad than that. And my focus will be on a particular type of holography called ensemble holography, which has been getting a lot of press lately. Um, let's go to the first page here. So there have been a number of, wait a minute. I have to turn the sound off on my iPad. Just give me a second here. Back to the introduction. So there have been a number of examples of that have come out in recent years in trying to understand better the holographic correspondence between quantum field theories in d dimensions and gravitational theories in d+1 dimensions. And in particular, it's been realized that there are several examples where the dual to a gravitational theory is not simply a conformal field theory, but a whole ensemble of several conformal field theories. And the prescription is that you need to average over these conformal field theories in this ensemble in order to get something which reproduces what you get from the bulk gravitational theory. And it's been thought that there's something fundamentally gravitational about this, the fact that these ensembles are arising. And that may be the case, but we're going to see lots of examples. We're going to see examples today where this happens, where you have ensemble holography, where it's you don't need to have a gravitational theory in the bulk, at least not a full gravitational theory. So some examples, which you might have heard about in some of your other seminars, include the duality between JT gravity in 2 dimensions, Joukiffe-Teitelboim gravity, and certain matrix model theories in 1 dimensions. These were proposed to be a holographic dual pair by Saad, Schenker, and Stanford back in 2019. And that proposal has led to a lot of developments and better understanding of gravity in this very minimal case of 2-dimensional gravity. Another example where ensembles have come up recently is called U1 gravity. And I will talk more about this, so I won't give an explanation of it right now. But that's where you have a U1 Chern-Simons theory in 3 dimensions. And that is supposed to be dual to a conformal field theory of the type that has been studied for a long time and the context of toroidal compactifications of strings. But basically, it's a free boson moving on a torus. And in that case, you need to sum over an ensemble of a whole collection of these toroidal conformal field theories in order to get the dual of the Chern-Simons theory. Another example, which is still more recent, is called Virasoro topological quantum field theory. That's a 3-dimensional theory, topological field theory, and it's supposed to be dual to the ensemble of all conformal field theories. So you take an average of some quantity like a partition function over all conformal field theories, and that should be equal to the bulk partition function of this topological quantum field theory with Virasoro symmetry. There are other examples that I don't have time to go into. But all of these have some things in common. They're all required to fix problems that arise with uh, uh, if you were trying to work with a single conformal field theory and study its dual that uh, which is the traditional way of thinking about holography. You start with a single conformal field theory and you have a gravitational theory in the bulk. Um, but what happens when you try to identify this single conformal field theory, if you're given a gravitational theory, is you find that this conformal field theory isn't really consistent. You'll find that its partition function has non-unitarity in it, like negative terms in it. There's a continuous spectrum, which you don't expect in a standard conformal field theory. And so the solution those problems were used as motivation by Saad, Schenker, and Stanford to propose that one should sum over a whole ensemble of boundary theories, in their case of matrix model theories. And in all these cases, the reason why ensembles are supposed to have something to do with gravitational bulk theories is that if you have, let's see if I can draw something here. Here's a picture of a manifold, a bulk manifold. Let's say it's in 3 dimensions just to be definite. And on the boundary, we have a 2-dimensional manifold. I'll call that sigma, some Riemann surface. We're working with Euclidean manifolds throughout this talk. So holography would normally say that if you compute the path integral of a gravitational theory on M3 with some boundary conditions corresponding to what's happening on the boundary with this conformal field theory, that path integral should be exactly equal to the partition function on this boundary theory. Partition function on sigma. So what we're saying is that on the in many cases, and perhaps in most cases, as far as we know, one should not be just summing over taking the path integral of a single conformal field theory sigma on the right-hand side, but an average over these things over a whole ensemble of um, of conformal field theories on the boundary. Let me just go on to the next slide. So this is still kind of an emerging technology. We don't know everything about these ensembles. There's no general theory of them. We don't know which gravitational theories in general require ensembles. We don't know which ensembles of conformal field theories correspond to gravitational theories. But we have several examples that we can look at and follow to get some ideas for how to generalize. So Maloney and Witten, yeah. So yeah, sorry, wait a second. How do I turn the pen off? Yeah. So there's some problems with these ensembles, specific problems, even with the ensembles that we understand very well. So for example, the U1 gravity theory that I talked about, where you have a U1 Chern-Simons theory in the bulk, and you have a free boson theory, conformal field theory, in 2 dimensions on the boundary. But the definition of that Chern-Simons theory, Maloney and Witten were quite puzzled by. And They weren't sure whether it should be a compact or a non-compact U1. They weren't sure how to regularize it in a way that made sense. And they said that they gave a fairly precise conjecture, which is that one should sum over a certain set of topologies called handle bodies of this Chern-Simons theory. But they didn't say why you should sum over those topologies and not other topologies. In the case of Virasoro TQFT, which I mentioned, which is supposed to be dual to the ensemble of all conformal field theories and is supposed to provide a real full-fledged model for topological gravity in 3 dimensions, or for dynamical gravity in 3 dimensions. In this case, the ensemble is not well defined. How do you define the ensemble of all conformal field theories? What's the measure on that ensemble? How do you weight the different conformal field theories when you average over them? And how do you regularize this very infinite sum over quantum field theories? So that's not a very well-defined proposal. And there are other problems with other examples as well. So, sorry. So here are some general questions that I want to keep in mind during this talk about ensembles, which we're going to try to at least give partial answers to. So first question is, when does an ensemble of conformal field theories, suppose someone gives you a collection of conformal field theories, how can you tell if averaging over those conformal field theories gives you something holographic, is equivalent to some gravitational theory in one higher dimension? So what conformal field theories should be included in this ensemble and how should they be weighted? Another question, suppose someone gives you a gravitational theory, how do you figure out what ensemble of conformal field theories that should be dual to? Does this always happen for gravitational theories or only for special ones? Does it happen in higher dimensions in particular? Suppose someone gives you a 5-dimensional gravitational theory. Is there a 4-dimensional quantum field theory dual to that? Further question, what topologies are we supposed to sum over when we take this gravitational theory and sum it over all possible topologies or just a few topologies? And finally, in general, there are infinite numbers of conformal field theories in an ensemble. There are infinite numbers of possible topologies. How do we regularize these infinite sums? So I'm going to actually try to give partial answers to all of these questions. We'll come back to them at the end. But before I go on, are there any questions that all of you have? Any of
Can I
you have?
ask one question?
Yes.
So in the original example of ADS5 gravity theory being dual to n equals 4 superangles, do we have an ensemble interpretation?
That is a really great question. So I don't have a complete answer to that right now. I do believe that in that case, and we can come back to that later, to that question later, the topology sum actually only does include one topology, which is the ADS5. And but the question about whether there should be an ensemble of n equals 4 gauge theories, that's an excellent question. I don't have a complete answer for that. But there are certainly cases where you could imagine there being an ensemble. And that has to do with what you mean by SUN.
Is it
So
like
there
the
are
global
various,
form of the gauge rule?
right. So there are various SUN type gauge theories. There's a standard SUN gauge theory where the gauge fields take their values in the adjoint representation of SUN. But you can also consider so-called SUN modulo ZN gauge theory. And that's inequivalent to SUN. Has a different spectrum of Wilson lines, and there are additional possibilities as well. Maybe you do SUN modulo some subgroup of ZN. Okay, so you get a whole collection of these SUN-like gauge theories, and maybe we should be averaging over that ensemble.
I see. So, can we think of it like this? There is a one-dimensional higher TQFT that captures all the global variance of this gauge group, where you can understand the entire, I don't know, it's called maybe orbifold groupoid, just from this
Sorry, I
five-dimensional
missed the
SIM-TFT.
sentence. Say it a
Like,
little louder.
there's this five-dimensional SIM-TFT that captures all the global gauge groups of the SUN gauge theory. So,
Yes,
when we have an ensemble, do we have like any interpretation in terms of this five-dimensional TQFT, and how does that relate to the ADS5
that's a
gravity theory?
fantastic question. Why don't you ask it again at the end of the talk? Okay. All right. So I'm going to discuss a general framework in which I think in attempting to answer the question about when does an ensemble uh, uh, of CFTs give you a holographic picture? When does or which gravitational theories correspond to ensembles? So the prescription is, I'm going to say, let's start with some topological quantum field theory in the bulk geometry. So that could be, and a topological quantum field theory is a field theory that depends only on the topology of the underlying manifold, not on the metric in any way. So if you have a two-point correlator in a topological field theory, it won't depend on how far apart the 2 points are, because that's a metric phenomenon. But it will depend on the overall global geometry of the space that you're living in. So let's start with a topological field theory. And a canonical example of that, which we'll focus on, is Chern-Simons theory in 2+1 dimensions. I'll come back and define Chern-Simons theory, which ones I'm talking about in a minute. But just so you have something in mind. And so if we have Chern-Simons theory in 2+1 dimensions, we consider putting it on a manifold with a two-dimensional boundary. If it's in 3 dimensions, we have a two-dimensional boundary with some fixed boundary conditions. The fields have some values on that boundary. And now we're going to sum over all topologies, all bulk topologies. In other words, all 3 manifolds that have that particular boundary condition on the boundary sigma. So we'll sum over a whole bunch of these different topologies. And by doing that, we're making this topological field theory into a gravitational theory. When quantum gravity tells us to sum over all geometries, well, normally that means integrating over all metrics. We don't have to worry about the integral over metrics, but we still need to include the sum over all topologies. So this gives us a very sort of stripped down model for quantum gravity, where we're just doing a discrete sum over topologies rather than an integral over all possible metrics. And we'll call this model for quantum gravity, we'll call TQFT gravity.
Can I ask something before
Yes.
we go on? Does this summing over process also correspond to summing over all Wessel-Witten theories at the boundary of Chern-Simons?
So you're getting a little bit ahead here, but right now I'm only talking about summing over the bulk topologies. Okay. I haven't started talking about summing over the boundary conformal field theory yet.
Okay, I see.
You're
Just
right to
bulk now.
anticipate that because what I'm going to eventually say is a sum over topologies on one side of a bulk theory will be equal to an ensemble average over, say, Wessumino-Witten conformal field theories.
Okay, I see. Thank you.
I have a question, sorry.
Yes, please.
Uh, when we talk about the bulk geometry, you don't put any metric, but as we also have boundary, you have to have an orientability defined, right?
Yes.
And
Yes.
how do you
Assuming in
accommodate
all
this
cases we
thing?
have orientable, we're dealing only with orientable manifolds.
Mhm. Okay.
All right. But actually, the orientation can be significant. For example, one example of a geometry of this type is you take a two-dimensional torus and you just fill it in. So you have a solid torus. That's an example of a three-manifold with a two-dimensional boundary. But if we took this torus and considered it with the opposite orientation and extended it into not into the interior of the torus, but into the exterior, we would get another three-dimensional manifold whose boundary was the torus. So the orientation does play a role in these sums, but in all cases, we're dealing with orientable manifolds.
So
Does that
how are we sure that when we integrate out, we get all the metrics? Because there are lots of papers who are also considering manifolds with non-orientable uh, non-orientable
How do we
manifolds.
know we shouldn't include non-orientable manifolds? Well, that's a very good question too. Why should we only include smooth manifolds? That's another good question, and I will partly address that last question. But in general, the question of which topologies should we include in this sum does not have an obvious answer and really should be derived ultimately.
Thank you.
Something
Thanks.
you need to prove. And so that was one thing that bothered us about Maloney and Witten's paper. They said to sum over, just to sum over these particular topologies called handle bodies, and they didn't explain why one shouldn't sum over other topologies as well. Okay. Oops. So keep trying to make the slide smaller so it will fit, but it's not doing it for me. Okay. Sometime. There it goes. Okay. So anyway, back to TQFT gravity. Again, start with a TQFT, sum it over all topologies. I've written that on the left-hand side of this equation here. And this is the path integral of the TQFT on a three-manifold M. And we're going to evaluate that path integral with fixed boundary conditions, summing over topologies, some set of topologies, which we'll have to figure out what that set is, whose boundary gives us the Riemann surface sigma. And what we are going to see in some examples is that the sum of a bulk topological theory over topologies is equal to a sum over some collection of conformal field theories on the boundary of their partition functions. Let's see an example. So I'm going to start with a fairly simple Chern-Simons theory. It's called AB Chern-Simons theory. It actually has two gauge fields in it. And that actually in some ways is simpler than having a single gauge field because if we did a standard Chern-Simons, Abelian Chern-Simons theory, that would have an anomaly, and we don't want to have to deal with any anomalies. So I'm taking two fields, A and B, and I'm using a Chern-Simons type of coupling between them. And we're integrating that over a three-manifold M, and the normalization is conventional. All right, and A and B are just abelian gauge fields. So this theory turns out to be trivial. First of all, it's free. It's just quadratic in the fields. It doesn't have any non-Abelian Chern-Simons term, which would be cubic in the fields. And it's exactly solvable. And you can, it's a topological quantum field theory, in fact, but it doesn't depend on the metric, but it actually doesn't even depend on the topology either. It turns out it only depends on what boundary conditions you set on the boundary of a three-manifold on sigma. Essentially what happens is the A and B fields, the modes associated with those fields cancel each other out perfectly. And so whereas a single U1 Chern-Simons theory would be able to detect some topology in M, this thing with the two fields, A and B contribute in opposite ways and cancel each other out. So the path integral over M, which is what we want to compute for holography, with some boundary conditions on A and B, which I denote A sigma and B sigma, it depends only on the boundary conditions for those fields. It does not depend on the topology of M at all. So you can think of this is a wave function here. A and B are the arguments of the wave function. And there's just a single wave function. Okay, you can't form other wave functions by considering other topologies or what have you. And so the Hilbert space of this theory is just one-dimensional. There's just this one wave function. And that wave function, the path integral of M over any topology, is equivalent to a particular free conformal field theory. It's equivalent to that path integral. Evaluating the path integral gives you exactly the partition function of a two-dimensional boson. Not a chiral boson, but a full non-chiral two-dimensional boson. A C equals 1 conformal field theory. All right. So that was fairly trivial. Let's do a less trivial example. Okay, so notice that, I'm sorry, what happened here? Did I just delete my last slide?
I think you did.
I did? How do I undelete it?
To reopen.
Okay, we just won't go back there. Yeah. Oh, Control Z maybe, Command Z. There it goes. Okay, good. So let's do a less trivial example. Okay, so first of all, this example here corresponds, actually I didn't say it, but it corresponds to a level 1 Abelian Chern-Simons theory. The coefficient here is quantized. In general, there will be an integer k, has to be an integer for gauge invariance. And so we're taking the case k equals 1 here. So now I'll consider a less trivial example, level 2, where k equals 2. And this turns out to be not quite trivial. The A and B effects don't fully cancel each other. And it turns out that it has non-trivial Wilson lines. The previous guy had no Wilson lines. The Wilson lines were all evaluate to just the number 1. But for this level 2 theory, it has Z2 cross Z2 Wilson lines. And the Wilson lines then can wrap around cycles in the 3-manifold, and they can detect its topology, some of its topology, not, you can't distinguish two arbitrary 3-manifolds from each other, but you can distinguish certain 3-manifolds and or classes of 3-manifolds. And so, for example, if the boundary of M is simply a torus, then those Z2 Wilson lines can wrap around the A and B cycles of the torus, like so. Okay, there's one cycle, and here's another cycle. Okay, and if you evaluate a Wilson line around one of those cycles, you'll get an element of Z2. That's what we're saying. So the Hilbert space here is actually 4-dimensional because you have two possible values for the Wilson lines around these two different cycles. And I'll make a side note because I don't want to go into a definition of Kitaev's toric code, but for those of you who are familiar with it, this field theory actually realizes the low energy sector of Kitaev's toric code, the vacuum sector. So yes, I already said this, the path integral indeed does depend on topology, but can only distinguish coarse features of topology using these Z2 Wilson lines. All right. And this fairly simple Chern-Simons theory, second simplest, I would call it our simplest non-trivial example, leads to our first example of ensemble holography, which we call U1 cross U1 AB level 2 Chern-Simons theory. Okay, so first we'll talk about topologies. We want to take this topological theory, put it on a 3-manifold, and then sum over topologies. And yeah, just checking how much time I have. Are we cutting off at noon, or do we run over? Is it okay to run over a little bit?
We actually don't have a time. You can go.
Okay. Okay. Well, I have to be somewhere at 12:30, so I can't go past then anyway. So let's talk about 3-dimensional topologies, in particular 3D topologies whose boundary is a particular Riemann surface. And for to definiteness, we'll take that to be a torus. Okay, so the simplest 3-dimensional topologies whose boundary is a torus are called handle bodies. The simplest example of those is a solid torus, where we just fill this in. Solid torus. Once you make the torus into a solid donut, what happens is before on the Riemann surface itself, there are two distinct non-contractible cycles. There's a basis, there's an A cycle and a B cycle. Of course, you can take linear combinations of those cycles as well. But the first homology group of the Riemann surface is 2-dimensional. It has two basis cycles. Once we fill it in, one of those cycles becomes non-contractible. It's the cycle that say goes around, goes through the middle of the torus. That can now be contracted in the solid torus. And that contractible cycle characterizes our handle body. There are other handle bodies when conform where other cycles are contractible. I already mentioned the handle body where you take the exterior of this torus. In that case, the other cycle that goes around the hole of the donut, that becomes contractible in the exterior of the torus. Okay, and there are additional handle bodies for all the other all the other cycles. Pick any cycle which is a combination of this red cycle and this green cycle, and there's a handle body associated with that where you say we're going to make that cycle contractible. So there's actually a whole infinite family of cousins of the solid torus whose boundary is a Riemann surface, which are characterized by this contractibility of a single cycle. And the modular group SL2Z of the torus maps all of these handle body geometries into each other. All right, well, we have a whole bunch of examples of three-dimensional topologies. I said that our topological field theory, this level 2 Chern-Simons theory, could distinguish some topologies, but it turns out it's not good at all at distinguishing all of these infinitely many handle bodies. It can just distinguish three classes of handle body topologies. Okay, one class includes the solid torus, another includes the exterior of the solid torus, and a third includes the exterior of the torus, and the third includes a handle body whose cycle A plus B would be contractible, and that's related to the solid torus by an ST transformation in SL2Z, just to be definite. So there are three equivalence classes of topologies. You evaluate this Chern-Simons theory in any any topology within one of these equivalence classes, and you'll get the same value as for any other topology in that equivalence class. So there's no point in summing over all topologies. If we're going to do a sum over topologies, it only makes sense to sum over these three distinct equivalence classes. If we tried to sum over all topologies, we'd get an infinity that we wouldn't know what to do with. All right. So we can evaluate this path integral, the TQFT. I'm not going to do that. It's technical, but it has a definite answer. Evaluated over each of these topologies. And what we're hoping is that we can write that as a sum of conformal field theory partition functions for some conformal field theories. So let's see what those are. All right, so what is our ensemble of conformal field theories going to be? In this case, the ensemble turns out to consist of just two conformal field theories. One is a free boson on a circle of radius 1, and the other is a free boson on a circle of radius 2. That's it. We denote their partition functions by zr equals 1 and zr equals 2. And those we can also write down explicitly. And again, I'm not going to do that, but you can look it up in any conformal field theory textbook, the yellow book, chapter 10. And we have an identity. Okay, you sum the path integrals over those three topologies I talked about, and that's equal to the sum of these two partition functions of conformal field theories. So this, as I said, is our simplest example of ensemble holography. We have the ensemble of these guys on the right, and we have sum over topologies on the left. Okay. You can see this in our paper with Aharoni and Demarsky. If you want
Can I
to
ask one question about
Yes.
this? So usually the wave function in a quantum mechanical setup is like invariant under a phase transformation. But I'm not sure if that's to say that holds for the partition function as well. So, I mean, is there any tricky business with identifying a sum over wave functions to a sum over partition functions?
You're worried
Because
about
it's like
the phase of the
partition
wave
function is
Yeah.
an observable, but the wave function is not. It's the square of the wave function that is observable.
Well, yes and no, sort of. So first of all, the partition function on the right-hand side here these are non-chiral partition functions.
Mhm.
They are but they do involve phases. So I'm actually saying that the phases on the two sides are equal to each other as well.
I see. Okay.
Yeah, it's a complete identity.
I have a question.
Yeah,
Uh, we know that the partition function for the boson on a circle is invariant under some duality transformations.
indeed.
Uh, uh, is there something that's related with this on the left-hand side?
Huh. Um, so
So in a sense, if I
yes,
restrict
so
the
yes, on the left-hand side, I'll say this is a very schematic equation, the way I've drawn it, but the left-hand side, each of these wave functions depends on boundary conditions. It has an argument, which is what's happening on the boundary. What are the fields doing on the boundary? And so if you make a duality transformation on the right-hand side, you're also going to, in those wave functions, you're going to be replacing, say, R by 1 over R in the boundary conditions. Okay. So you sort of got to build a T-duality into this equation. But you're not imposing anything. It fits in a very natural way. But the T-duality only, yes, it affects the boundary conditions of the wave functions on the left-hand side. And the claim is that maybe not each individual wave function, but the sum of these three wave functions must be invariant under that duality,
Mhm, mhm.
under
So,
T-duality.
okay, so the duality invariance, how should I say this? The total wave function, let's say, should be invariant.
The sum of the wave functions on,
Okay.
yeah, summed over topologies should be invariant. Absolutely.
Okay. So it's somehow you changes the boundary condition or plays with the boundary
Yes, it
condition.
has an effect on the boundary conditions, but then you see if you just plug in and see what happens when we change the boundary conditions in this way,
Mhm.
you find that that sum is invariant.
Okay, then let's say I take the quotient of the moduli space for the boson on a circle. So I'm basically discarding the points that are also dual to some other points in the moduli space. Do I get rid of any portion of wave function on the left-hand side?
No,
Okay.
no. In fact, well, on the right-hand side, these values of the radius here, I've chosen them to be in one particular fundamental domain of the moduli space.
Oh, okay. Okay.
Okay.
So R equals 1 is not the self-dual.
No, R equals 1
Okay.
over square root of 2 is self-dual.
Okay. Thank you. Thanks.
Yeah, good point. All right, let's generalize this. Okay, I want to now take many copies of this A-B Chern-Simons theory. So we'll have a lot of different gauge fields, A and B, indexed by I and J. And I think yeah, I made this the wrong way. I think that way I'm indexing, maybe perhaps I should replace B by A. But anyway, this generalizes what I had before. And Kij is now a matrix replacing the single integer which described the level of the Chern-Simons theory back when I just had an A and a B field. Now we can have a whole matrix of cross couplings between the different A and B fields. This is called a K matrix. You might have seen Lagrangians like this if you studied the fractional quantum Hall effect. And it rises in other contexts as well. But this is just a convenient generalization, an easy generalization to make of the case of a single A and a B field. The previous cases I had corresponded to a K matrix of 0, 1, 1, 0, and because the off diagonal means we're only coupling A to B, we're not coupling A to itself. And level 2 was 0, 2, 2, 0. Okay. So the level's been replaced by this matrix Kij. Now, when the determinant of K is equal to 1, we have a situation similar to the level 1 case that we discussed above. So if K was, say, a bunch of copies of this 0110, or maybe it has an E8 self-dual, even self-dual matrix in it. In that case, you would have a trivial theory and no dependence on the three-dimensional topology. And the path integral in this case, when the determinant is 1, is dual to a single Narain theory, not an ensemble. When the determinant of K is greater than 1, however, that corresponds to our higher level case, and we must sum over an ensemble of Narain conformal field theories. Sorry, did I say what a Narain theory was yet? I didn't. And conformal field theories of free bosons. And I'm going to talk about what that conformal field theory is in just a second. But let me say a couple more things about our Chern-Simons theory. So this is I just repeated the action for the Chern-Simons theory, general Abelian Chern-Simons. Kij is it's a matrix. It defines a 2n dimensional lattice. It's 2n by 2n. And that lattice lives in Rn comma n. Because a matrix like this here has signature 1 comma 1. That lives in R. That would define a lattice in R2, R1 comma 1. But more generally, this K matrix is going to define for us a lattice in Rn comma n. What is that lattice? You just take your matrix and you multiply it by a general, wait a second, pair of integers. And that gives you that generates a lattice in 1 plus 1 dimensions, with a natural Lorentzian norm given by this matrix itself. All right, so it's a 2n dimensional lattice of signature n comma n. It has a dual lattice. A dual of a lattice is a set of all points in Rnn whose inner product with every element of our lattice lambda is an integer. That's called lambda. Well, T doesn't mean transpose, it means dual in this context. It's generally bigger than lambda because lambda is an integer matrix, and so any point in lambda, inner product with any other point, gives you an integer. So lambda is included in the dual lattice, and there's a quotient you can form, lambda transpose modulo lambda, and it's called the discriminant quotient. Anyway, that's all latticeology. It's not so important for what we're going to discuss, but just keep in mind that there's a lattice, and the dual lattice is also going to play a role. So I claim that in general, this type of topological theory can distinguish a finite set of types of topologies, a finite set of equivalence classes. In the simplest cases, actually, that corresponds to where this determinant of that K matrix is the square of a prime number. It's actually always going to be a square. In that case, the topologies that arise in the topology sum are all handle bodies, finite set of handle bodies. That's like our level 2 case. Okay, in that case, the determinant of the K matrix, where is the K matrix? Of this K matrix here was 4 or minus 4, and which is the square of a prime. Okay, and there the topologies were all handle bodies. And what's going to happen when it's the square of a larger prime number is you'll have many more handle bodies. And actually, this is still true that you get handle bodies if this number is the square of a product of different primes. More generally, though, if K is some general composite, if this determinant is some general composite number, you'll get additional topologies besides handle bodies. You'll get singular topologies, things that you wouldn't even call a manifold, and that must be included in the sum. So this is actually telling us already that summing over handle bodies or even summing over smooth topologies is not enough in general. And you can deduce, given Kij, given a K matrix and a theory of this type, you can deduce which topologies should be included, and then we can perform the sum over those topologies. And I'm not going to tell you how we deduce. That's a long story in a couple of papers, but just keep in mind that there is a way of doing that, and it gives you a definite answer. So the question is, so if we're given one of these theories and we sum it over all of these inequivalent topologies, is the sum going to be dual to an ensemble of conformal field theories? So let's talk about what should be the dual ensemble of these Abelian Chern-Simons theories. So first guess is maybe we should take a boson living on the torus, living on a space defined by the lattice lambda. We'll just take the Lorentzian space Rn comma n that lambda lives in, and we'll mod it out by lambda, and that gives you a torus. Okay, just like modding out the plane by the integer points in the plane gives you a standard square torus. This will give you a torus. I mean, a higher dimensional torus, and 2n dimensional torus. Okay, but it turns out in general that would not give you a consistent conformal field theory. In order to have a consistent theory, we need this space, this 2n dimensional torus, to be defined by a self-dual lattice, a lattice for which lambda equals lambda dual. And that corresponds, for example, to the case determinant of K equals 1. That would automatically give you a self-dual lattice. All right, so but these conformal field theories of a boson living on a torus that comes from a self-dual lattice, they are well known in string theory literature. These are what give you toroidal compactification of strings. They were discovered in, I think, 1987 by Narain. So they're called Narain CFTs. And so our first guess was wrong. But there is a way to get us one of these consistent Narain theories, which is to, hold on a sec. I'm getting a little bit of an echo, and I just want to, wait a minute. That's wrong. I want to turn off the audio on here. And I can't do it. Okay. Let's go back. Okay, so there are, the way we're going to fix this, the fact that we didn't get a consistent conformal field theory, is we're going to construct a self-dual lattice. There are lots of self-dual lattices, in fact, that live in between the original lattice lambda and its dual lambda transpose. So we're going to consider a self-dual lattice of that type. As I said, there are many, and all of them lead to equally good CFTs. And we could consider the ensemble consisting of all of these consistent CFTs. Doesn't really make sense to just pick one of them. If you're going to pick one, you might as well pick all of them. Okay, so this gives us a natural ensemble, and that's our candidate for what should be the ensemble of CFTs dual to our bulk Chern-Simons theories. And you can compute exactly the partition function for each of these theories. That's well known. You can, again, look that up in the yellow book. And you can average over the ensemble. There are actually just a finite set of these self-dual lattices that lie in between lambda and lambda dual. And so we'll compute the sum over the average over this finite set, this finite ensemble. And we find that indeed it is equal to the sum over topologies of the Chern-Simons theory. All right. Let's see. There. So just to restate the result that we get, we started with this general abelian Chern-Simons action with a matrix K. And given that action, you take that, you do the path integral over M, and you sum over topologies, a certain set of topologies, whose boundary gives you sigma. Okay, again, we're just going to take the topologies that can be distinguished from each other by this particular topological theory. Sum over that finite set, and that's equal up to some proportionality. For completeness, I'll put a number there. It's equal to sum over a set of conformal field theories on this torus defined by the self-dual lattice that lives in between lambda and lambda transpose. Okay, where lambda is the lattice defined by this K matrix. Sum up their partition functions. That's equal to the sum of these wave functions. All right. A couple of fine points. The sum over topologies here. On the left-hand side, let's call these topologies M sub I. There could, in principle, be some constants, alpha I, weighting that sum over topologies. And what happened there? Anyway, there's a sum over, yeah. So we don't know what the weighting of the topologies is. Well, we do know, but one has to compute that, and it's a tricky computation. But at least in the case where the simple case where the level is prime, these weights are all equal to each other. Okay. Similarly, you might worry about what is the weighting of these theories on the right-hand side. Well, they're all similar enough to each other that, at least for this class of theory, the weights are all equal. So This is a great example, I think, of beautiful example of ensemble holography, where you can compute everything exactly because on both sides of the holographic duality, you're talking about free fields. And I think it's already taught us a lot about how these ensembles work, but there's certainly more to learn, and certainly these Abelian free theories are a very restricted class. So I'm going to talk about more general theories in a minute, just briefly, but let me also say something about an important limit you can take. So you can take the limit where this K matrix approaches infinity, where the determinant gets very large. Okay, and that's kind of like a large C limit. It isn't really, but it's basically it's a semi-classical limit is the right way to describe it. And in this limit, it turns out, well, the Chern-Simons theory is getting more and more complicated. We started out at level 1, we couldn't detect any topology. Level 2, we could detect 3 different types of topology. As the level becomes large, you detect more and more topologies, and when it goes to infinity, you can actually distinguish all different handle body topologies. So, so all handle body topologies get included. And what happens, there's an infinite number of them, and each of them corresponds to sorry, on the CFT side, we also end up with an infinite ensemble. You get, turns out, you get the entire moduli space of toroidal compactifications of Narain CFTs, which is a big continuous moduli space. And you can write it down. We know the measure on that space. And that moduli space gets covered, that's just schematically, gets covered by all these discrete CFTs. It gets covered uniformly in a way that reproduces the correct measure on that moduli space. All right, so in this limit, we have that the sum over all handle body topologies should be equal to the average of all these Narain CFTs over their moduli space. That's exactly what the original claim of Maloney and Witten, and also Afghani, Jetty, Cohn, Hartman, and Tajini is, which I mentioned earlier. This is the U1 gravity claim, or U1 gravity conjecture, that you have this exact duality between bulk Chern-Simons summed over handle bodies and boundary Narain theories integrated over moduli space. But there were, as I mentioned, a lot of problems in their paper with regularizations, with how do you define this U1 gravity exactly? And what we have now here by defining it as this large K limit is a regularization of U1 gravity, where all the sums everywhere are finite. There's no problem with that. And we know exactly what we mean by this U1, whether it's compact or non-compact. It's tricky, actually. It's best defined in this limiting fashion. It's sort of in between the two of them. I could say something about the limits of large genus of the Riemann surface and the large n with a number of U1 factors, but I'm going to skip that because I want to talk about even more interesting stuff. So, before I go on to generalizations, questions?
Can I ask one?
Yes.
So, so far in the story, we took the K matrix to have integer entries, but if we have like fractional, rational numbers in the entries, we will have some relation with the fractional Hall effect. How will the story change in that case?
Yeah.
Like,
We don't do that because you put fractional numbers in there, you have to give up gauge invariance.
mhm.
Um, and and generally, and you're absolutely right. You for the fractional Hall effect, you can take rational numbers there, but in that case, you don't have duality to an exact conformal field theory, despite claims in the literature. Um, and there may be a way of doing that, but I don't know how to do it. Great
So it's
question.
not a well-defined thing. It's too
What's that?
vague. So
Huh?
it's not a well-defined thing. It's too vague.
It's what?
It's too vague, like not well established.
Right, right. Mhm.
Okay.
I mean, I think certainly, as I said, there's a literature on CFT dual to fractional Hall effect, but I think that's missing the whole boundary, the whole ensemble issue. I think one needs to sum over ensembles there.
Okay, thanks.
And it's not clear what summing over ensembles means in a condensed matter context.
I see.
All right, so we talked about abelian Chern-Simons. What about non-abelian examples? So suppose we have some general topological field theory. We demand that it be non-anomalous. Otherwise, you don't have this clean separation between bulk and boundary. You would have the bulk and boundary coupled to each other in an anomalous theory. But non-anomalous topological theory, like the ones we've been talking about, like these AB theories, we're going to start with one of those and sum over topologies, and that's going to give us our TQFT gravity theory. And so we again are going to ask, is this ensemble a dual to an ensemble of CFTs? And we also want to know, we're given an ensemble of non-trivial, not free CFTs anymore, interacting CFTs. Is that going to be dual to a bulk gravitational theory? So an example that I mentioned already is this Virasoro TQFT. I'm not going to say much more about it, but that is maybe our eventual goal is to understand that theory better, because that should be dual to the ensemble of all CFTs. Right. Just a sec. So let's talk about one of the simplest non-trivial interacting CFTs, the Ising model. Okay, so the Ising model has C equals 1/2. Probably you may have seen the Ising model discussed. It has 3 non-trivial operators in it, and what you may not have seen is that it is dual to a particular topological field theory, which is called the Ising TQFT. And an Ising TQFT is a model for strongly coupled gravity in 2+1 dimensions. C is very small, and small c means that the coupling in the gravitational dual is very, very large. If you want to get a weakly coupled theory of gravity, more semi-classical gravity that has the usual features we associate with Einstein gravity, like a metric and so forth, we need large c. We need to study the limit of large c. So a natural way to do this, what happened here? I'm sorry, there's a glitch here. Okay, this bit shouldn't be in my file, but I can't get rid of it at the moment. So a natural way to get a large C theory is to take the tensor product of many Ising models. And there's a paper that tried to do this by Castro, Hartman et al. They took tensor powers of Ising models. They took also higher minimal models, and they found that it didn't work. It didn't give you a gravitational dual. Didn't give you a good dual. It could not have a holographic dual. It would be an inconsistent um, bulk theory. So what we think was missing in that paper, in those arguments, is that they really should have been taking an ensemble of theories. If you take an ensemble, then maybe averaging over that ensemble will give you a nice bulk dual. So there are other ways to build CFTs out of, if you have n copies of the Ising CFT, you can put them together in various ways. And essentially using some types of orbifolding techniques. And in this way, you can form a natural ensemble of CFTs that are built out of n Ising models. Okay, this is similar to what we did before. We took a single boson and we took n single bosons to generalize that. So this forms a natural ensemble, and we can sum over this ensemble of CFTs with appropriate weights, and that turns out to be dual to the Ising TQFT in the bulk, summed over a set of topologies, also with appropriate weights. The simplest case for level 2 for two Ising models, it turns out that the two theories in the ensemble are the Ising tensored with itself. We call that Ising squared. And then there's also another theory with C equals 1 that you can make out of Ising models, which is called the Dirac theory, Dirac CFT. So we take a particular combination of those, they have non-trivial weights, and that should be equal to a sum over topologies. Again, in this case, it's going to be 3 topologies of some seed wave function, some particular wave function. And so this is our Ising model, simplest example of our Ising model duality. So yes, the answer is we can generalize ensemble holography to more complex CFTs, and one still ends up with a sum over topologies in simple cases. Okay, another question. What about higher dimensions? So we took a look at 4-dimensional Maxwell theory. That's kind of a natural generalization of a 2-dimensional boson to 4 dimensions. It has a lot of properties in common. It has S-duality, similar to the T-duality of the 2-dimensional boson. It's also a scale invariant theory. So there's its Lagrangian. You notice we're allowing including a theta term, and that means that we're allowing magnetic field configurations as well as electric ones. And we're going to put this on some 4-manifold, M4. And for a general 4-manifold, depending on what the topology of that 4-manifold is, we can have magnetic and electric, monopole fluxes. We can have a whole collection of non-trivial U1 bundles over M4 of non-trivial, topologically non-trivial gauge configurations. So our partition function will need to sum over all those topological configurations. And you can write the partition function down exactly. I didn't do that because it's kind of long. And you can verify that it has exact electric magnetic duality. Okay, so if you arrange the couplings theta and G, the theta term and the gauge coupling, the Maxwell coupling G, into a single complex coupling tau, like so, then electric magnetic duality takes tau to -1 over tau. There's also a symmetry under tau goes to tau plus 1, which corresponds to theta goes to theta plus 2 pi periodicity of the theta angle. And they generate a full SL2Z duality group. So we can ask, does this Maxwell theory have a holographic dual? And the answer is there is indeed a Chern-Simons-like theory in 5 dimensions that looks like this. It involves a 5-dimensional epsilon tensor, and there are two form fields, B and C, that appear. Okay, this is the generalization to 5 dimensions or 5-dimensional analog of our AB Chern-Simons theory. It turns out this is this 5D theory is a trivial Chern-Simons theory, but similar to our level 1 theory, but it can detect topology. If you put in a level here, if I added a k here, an integer k, and made k 2 or 3, some non-trivial integer, then I could detect topology using this theory. We can generalize this like we did before to n copies of this Maxwell sort of theory. I'll call that U1 cross U1 to the nth gauge theory. Why U1 cross U1? Well, I didn't spell this out before, but this theory we talked about here, the Maxwell theory, actually is this is like well, there's electric and magnetic stuff going on in here, and we can think of this as a U1 electric cross a U1 magnetic gauge theory. But that's not exactly right, because in general, if you want to write down this action, I've written down an action, maybe the magnetic action, but there's a dual electric action that would have a similar form, which would have the inverse coupling. So what we haven't specified in this action here is which Wilson lines of the gauge field we're allowing. And if you allow all the electric Wilson lines, then they prevent any magnetic Wilson lines from appearing. If you, because of anomalies, if you allow magnetic Wilson lines, then you prevent electric Wilson lines from appearing. So there are actually multiple theories here that described by this action that are or when we say 4D Maxwell theory, it could be multiple things. It could be an electric Maxwell theory, a magnetic Maxwell theory, or a dionic Maxwell theory. Okay, so here we're generalizing now to n copies. And as I said, in general, we could gauge either electric or magnetic, or I guess dionic U1 in each factor. There's a large set of different possible gaugings then of this theory, where we say in each factor whether we're going to take electric or magnetic, do even more complicated things where you take charges which are in you allow Wilson lines with charges in several of these different factors. And there's a whole multiplet of possible gauge theories here. So it's a whole ensemble. So we've got an ensemble. The natural thing to do is to sum over that ensemble. And the claim is that if we sum over this ensemble of electric and magnetic gauge theories, it will be dual to one of these Chern-Simons type theories, these two-form theories, summed over an ensemble of 5-dimensional handle-body-like topologies. It sounds complicated, but if I wrote it all down for you, the equations would be exactly the same, and I mean exactly, as the ones we had in 2 and 3 dimensions. So it's actually kind of remarkable how similar the 4D theory, this 4D theory and the 2D theories are. There's a reason, which is they can both be derived from some parent 6-dimensional theory, which if you compactify that on a 2-dimensional Riemann surface, you get this 4-dimensional gauge theory. If you compactify it on a 4-manifold, you get a 2D boson. So yes, ensembles do exist in higher dimensions, and this is a beautiful example of one. I'm almost done. Let's go back to our original list of questions about ensemble holography. First question was, which ensembles of conformal field theories have holographic duals? The answer, which I didn't fully explain, but I'm putting it here just so you see there is a definite answer, is that ensembles are generated by sums over consistent gaugings of global symmetries. And actually, it's global one-form symmetries in the Chern-Simons case and global two-form symmetries in the 5D case. Second question, when is a gravitational TQFT dual to an ensemble average of CFTs? We believe the answer, we conjecture the answer is always. You just got to find the right ensemble of CFTs. But I don't think we'll really know the answer until we understand Virasoro TQFT better. As for when does this generalize, say to higher, in particular, does this happen in higher dimensions? We have a definite answer to that. It's certainly yes. What topologies are we supposed to sum over? The answer is sort of all topologies, but in general, this sum over all topologies is redundant. And that redundancy would lead to infinities. So we throw away the redundant topologies, and what's left are, in these finite level cases, is a finite set of topologies. Finally, how do we regularize when we have infinite numbers of CFTs and infinite numbers of topologies? Well, we don't know the general answer to that, but we know, at least in the U1 gravity case, that we can regularize that by taking limits of finite ensembles. And our goal would be, for understanding Virasoro TQFT better, would be to express that as a limit of a set of TQFTs with finite numbers of degrees of freedom. And the CFT, the sum over all CFTs, we would replace that by a finite sum over some discrete ensemble, which converges in the large level limit to all CFTs. But we don't have a full answer to this yet at all. Further directions, well, there's a number of, I just threw a few up, there are more, but a few obvious further directions. One is to extend our 2D, 3D correspondence to more complex CFTs and TQFTs. Natural thing to look at would be Wessumino-Witten models, dual to non-Abelian Chern-Simons theories, and that would be, actually, if we could really understand that, that would be a big step towards understanding the Virasoro TQFT. Okay, another direction would be to take another look at the correspondence matrix theory and JT gravity in 1 and 2 dimensions, and try to understand it in our terms and as a dimensional reduction of the 2D, 3D case, which we understand pretty well. Finally, we'd like to be able to generalize this to non-Abelian gauge theories in 4 dimensions. So far, I only talked about Abelian gauge theories. And in order to do that effectively, we're going to have to talk about some gauge theories which have some high degree of solvability. And the place to start there would be n equals 4 supersymmetric gauge theories. And that takes us right back to a question that was asked earlier and to the original example of holographic correspondence, which is between n equals 4 SUN and string theory on ADS5 cross S5. So that's where we would like to be, but I don't know when we're going to get there. That's it for my talk. Thank you for listening so long.
Hello. Can you hear me? I have
Yes.
some questions, if I may.
Sure.
So, first of all, I want to ask about 2 directions of the duality. So, when we have, let's say, ADS CFT with this gay PKV KW dictionary, we have the fortunate.
I'm sorry, what with the what dictionary?
GPKW dictionary with the for
Right.
ADS-CFT at least. So
Okay.
with that, we are able to find duality in two sides by doing the integrating in. But in this case, we have the average of the partition function, which will give us eventually some number. So how can we show that this duality is two-sided with this ensemble of CFTs, and how can we understand which CFT we should use to find the integration? So I'm confused about that, if it's relevant to this.
So, yeah, one thing I only talked about partition functions.
Yeah,
I didn't talk about correlation functions.
yeah,
You can extend to correlation functions by considering some slight extension of this to a generating function instead of a partition function.
okay.
And then you take derivatives, you put in an external current, take derivatives with respect to the current, and that will give you correlation functions.
Um,
But you can also think of the correlation functions as being of local operators,
okay,
as in the bulk being two boundary points joined by a Wilson line ending on those boundary points. And that's actually a difficult thing to compute in the
yeah,
Chern-Simons theory. So
yeah.
we haven't really fully explored the correlation function correspondence at that level.
Also, I wondered that since we worked with this 3D, 2D site with the Chern-Simons, AB Chern-Simons, do we have any results on, at least for the entropy, like Cardi entropy or asymptotic density of states of this?
Oh, yes. So that's been studied. Yes. In fact, it's not a Cardi-like entropy for
Okay,
those simple abelian theories. Instead of the entropy uh, growing exponentially with level, the it grows polynomially,
okay.
and
And
that's explained in some detail in discussed in some detail in a paper that I wrote with Demarsky called on the holographic interpretation of code CFTs.
okay, maybe I should check that. And also, can we come back this AB Chern-Simons slide if you can?
The original one?
Yes, the original one. Yeah. Uh,
Okay.
yeah. I wondered that. So when we have this non-Abelian Chern-Simons theory, at least we can go somehow find this double ZW model by just looking at this SL2R representation of this A field, and then equating them on the boundary with the chiral and non-chiral side, and find this sigma model at least. But in here, A and B have different degrees of freedoms. And if we try to, at least, let's say from here, we try to do some dimension reduction to some kind of a BF theory, at least for the JT gravity side, this the curvature will come from A somehow, and B is again have another degree of freedom. It's in another gauge field. So on the boundary, we have to find somehow a dynamical boundary condition so that we can have a dynamical boundary theory. But if we do that, then A and B should be at least somehow in some components should be equivalent on the boundary. And that means they don't have these different degrees of freedom. And then when we come to path integral side, we have two different path integrals for dA and dB. And so how come we know the boundary conditions so that we can have this path integral on the boundary as two different fields? So I just confused about.
Yeah, you'll have boundary conditions for A and for B,
Yeah.
but not actually for all the degrees of freedom in A and B. This
Okay.
is rather a technical point, though.
Okay.
So there are some free degrees of freedom,
Yeah.
which give you some dynamics that you're worried about. But the degrees of you fix basically you fix half of the degrees of freedom, and and those boundary values of A and B are the moduli of your dual theory of your CFT.
Okay, okay. So thank you. That's all my
Okay, sure.
questions. Thank you for your answers.
Okay, very good. Other questions? I said I have to be somewhere at 12:30, but I can push it off another couple minutes if there are more questions.
Can I ask one question in that
What
case?
chat? There's a
Sorry.
question in the chat that just
Okay, sorry.
came. How do you compute the weights? So the weights of the topologies in the sum over topologies. Yeah. So yeah, we have a paper about that called uh, um, what is it called? It has ensemble holography in the title. It's with Demarsky, and um, it's actually it's. I'll just give you a very rough idea, but um, it turns out. Suppose we have a genus one Riemann surface as our boundary. Okay, and we want to know what are all the bulk geometries we have to sum over, topologies we have to sum over with that particular fixed boundary. It turns out that the best way we found to compute what those topologies should be and what the weights should be is to oh, I'm running out of batteries here. Let me just connect this to my iPad so that we don't lose our signal there. Okay. Oh, yeah. So the best way we found to compute those topologies and those relative weights is actually to go to higher genus Riemann surfaces. Because it turns out in the limit of infinite genus, we know exactly what topologies we should sum over in that case. You should just sum over handle body topologies and nothing else, and all with equal weights. It's remarkable that there's this simplification when you go to infinite genus. So basically what you want to do is you want to reduce from infinite genus down to finite genus, and that naturally gives you the weights. But if you want more details, I think you better look at the paper. It's probably you can tell the answer is a bit technical. Just a sec. What's wrong here? I'm sorry. There it is. Okay. I think we did lose the iPad. Oh no, there it is. Okay, back. Okay. Anyway, it's this it's a very well-defined genus reduction procedure, but it's not simple.
Can I ask one quick question?
Sure.
So, you mentioned like the Virasoro TQFT a lot, and it's a holographic tool of the average over conformal filters. What if we don't have all the conformal filters, but only the rational conformal filters, because they are simpler and they are a bit more compact in terms of the moduli space?
Right.
So what kind of a Virasoro TQFT do we get in that case? Like, can be computed
Right.
explicitly?
I mean, that's an example of maybe of what I was suggesting, which is to really understand this full duality, we need to have some maybe limiting sequence of theories which can approximate it. Now, any irrational, as far as I know, at least all examples I know, any irrational conformal field theory can be approximated by a sequence. Nah, that's not going to be true in general. No, no. So anyway, it's possible, but we just honestly don't know enough about the space of all conformal field theories to even make a conjecture there. But it's possible that that would just doing rational conformal field theories would be a bit more tractable than all CFTs, and that it might um, be a good approximation to the full answer.
Uh, anyone else have any questions? Maybe I can supplement.